So in this video, part 2 of our natural logarithmic function, I'll work through these 4 examples with you so you can see a little bit more in detail how this new rule for taking a derivative of the natural logarithmic function will work. So similar to where we left off, we now have ln of x cubed. So we have an inner function here that's inside our ln function. So as we do this, we will have to then use our chain rule. So the derivative of f of x is equal to, we start with our outer function, derivative of the ln function is 1 over the argument, so in this case 1 over x cubed, and then we have to multiply by the derivative of the inner function, and the inner function is the argument of that logarithm, so we end up with 3x squared. If we simplify here, we can divide out 2 of our x's, and we end up with 3 over x for our derivative. We can also now start to incorporate this rule with some of our other rules. Here I have a quotient, so we will have to apply our quotient rule as we take our derivative. F prime at x equals derivative of the top, so that would be the derivative of a natural logarithmic function. So we have 1 over the argument multiplied by the derivative of the argument, which is 2. So there is the derivative of the top multiplied by the bottom minus top times the derivative of the bottom and then we'd have that all over our denominator squared. If we simplify these terms a little bit, in that first term I can divide the 2's out. I can also divide one of the x's out, so that would then give us here x squared minus, and I'm going to rewrite this as 3x squared ln 2x all over x to the exponent 6. And then lastly, we can look at all 3 terms here, and we can divide out an x squared here, an x squared here, and an x squared here. And if we do that, we end up with 1 minus ln 2x all over x to the exponent 4. In our third example, this time it happens that the inner function, our argument, happens to be a binomial. That's fine. We still apply the rule in the same way. The derivative of our outer function, our ln function, would be 1 over the argument. So it's 1 over that binomial. And then we would have to multiply that by the derivative of the inside. So the derivative of the inside, term by term, since this is a polynomial, would be 2x plus, and now this is where we can also start to incorporate the derivative of that natural exponential function as well from our last lesson, in this case a relatively easy one. The derivative of e to the x is e to the x multiplied by the derivative of the exponent, which is just 1. And then we can clean this fraction up a little bit. If we multiply these together, and we have 2x plus e to the x all over x squared plus e to the x. Be really careful that we don't try to divide these out. Remember that if we are reducing a fraction, we need something that will divide out of all 4 terms here to be able to reduce this. Since nothing will divide out of all 4 terms, this is our reduced and final answer. And then our last example here, I'll walk you through a similar example to what we did in our previous note, and that is we can now take these new derivative rules and use them to find equations and slopes of tangents. In this case here, the function I've given you is written implicitly, so we will have to also then incorporate these new rules with our implicit differentiation rules as well. So if we start with our function here, x e to the exponent y plus y ln x equals 0. If I differentiate here implicitly, a few things that I do have to watch. I do have a product rule here. We have 2 separate terms, and I also have another product rule here. So if I start with this first one, I'm going to say derivative of the first. which is 1, multiplied by the second, e to the y, plus my first function, x, times derivative of the second. Derivative of the second would be e to the y, multiplied by the derivative of the exponent. Derivative of y would be dy by dx, plus my second function, so derivative of the first would be 1 dy by dx, multiplied by the second, ln x, plus the first function, which is y, multiplied by the derivative of the second. Derivative of that ln function then would be 1 over the argument, or 1 over x, equals 0. If we now try and simplify this, any term that has dy by dx, I'm going to leave on the left-hand side. We can also do a little bit of factoring here as well. I would have then dy by dx being multiplied by x e to the exponent y plus ln x, so that's these two terms, and I've factored out the dy by dx, would equal then negative e to the exponent y if I move that term to the other side, and minus this term here, which is y over x. Lastly, if we isolate dy by dx, dy by dx then will be negative e to the exponent y minus y over x, all over x e to the exponent y plus ln x. So remember that this now, our derivative is the slope of the tangent. So specifically, we want the equation of the tangent. So first we need the slope of the tangent at this point, and this point being on this curve. So then I'm going to say, therefore, dy by dx at x equals 1, y equals ln 2 would equal negative e to the exponent ln 2 minus ln 2 over 1 all over 1 e to the exponent ln 2 plus ln of 1. Now here you can either use some of your evaluating techniques from advanced functions when we're evaluating logs and exponential functions. If you're really stuck, you can actually evaluate some of these things with your calculator. I'm going to try and stay away from decimal answers, so if things give me decimals, I'm going to end up just leaving them them as e's and lns in my expression. This first one does actually simplify quite nicely. Here you will get negative 2 minus, this does not evaluate nicely, so I'll leave that as ln 2 all over. This will evaluate quite nicely to just 2, and ln of 1 evaluates quite nicely, that is 0. So in the end here we end up with the slope of our tangent being negative 2 minus ln 2 all over 2. Not necessarily a nice number, but an exact number. Now that we have our slope, we're now going to sub this in to our equation to figure out what our y-intercept is. So I'm going to say, let's then sub in that our slope is equal to negative 2 minus ln 2 all over 2. And we'll sub in that x and y are equal to 1 and ln 2. If I sub that into y equals mx plus b, we would then get here y, so ln 2 equals m times x plus b. Isolating for b, we would have b equals ln 2 minus that crazy fraction If I want to add these together, I'm going to need a common denominator, so I'm going to change this part here to be 2 ln 2 over 2 as I get a common denominator, And I'm going to distribute that negative so that this becomes plus 2 and plus ln 2 all over 2. So there's our value of b. And now that we have a common denominator, we can actually add these together. Okay, common denominator is 2. I can actually collect some like terms. I have 2 ln 2 plus another ln 2 will give us 3 ln 2 plus 2. Lastly then, our equation, not very nice looking. Y equals m, that was this mess over here. So negative 2 minus ln 2 all over 2. So there's m, x plus, and the b value, also not very nice looking. But there is the equation of our line, y equals mx plus b, with a very messy looking m and b value. Hope that helps. Again, as always, please make sure that if you have any questions, you are emailing me, and please make sure you are attempting and completing the assignments. Have a good day, guys.